Space is big, really big. It's hard to imagine anything bumping into anything else out there. But, every now and then, the universe throws a curveball. Planets, those massive balls of rock and gas, can collide. These events are rare but leave a lasting impact on the universe as we know it. Imagine the energy released when two planets, each with its own gravity and momentum, smash together. The results are spectacular and catastrophic, reshaping the face of planetary systems. These collisions are not just destructive, they are also a force of creation, playing a role in the formation of planets and moons. These cosmic events, though seemingly distant, can offer valuable insights into the formation and evolution of our own solar system. By studying the scars of past collisions, we can piece together the history of our cosmic neighborhood, and maybe even understand the conditions that led to our own existence. Planetary collisions are governed by the fundamental laws of physics, particularly gravity. In the vast expanse of space, gravity acts as a cosmic choreographer dictating the movements of celestial bodies. Planets, drawn by the gravitational pull of stars, and often influenced by their neighboring planets, can be nudged into different orbits over millions of years. Sometimes these orbital shifts lead to close encounters and, in extreme cases, collisions. These collisions are not mere fender benders, they are high-speed impacts with tremendous energy involved. The kinetic energy, the energy of motion, is released upon impact, generating intense heat and causing widespread melting and vaporization. The consequences of such collisions depend on a variety of factors, including the speed, angle of impact, and the size and composition of the planets involved. A head-on collision would release more energy than a glancing blow. Similarly, collisions involving larger planets would be significantly more energetic than those involving smaller ones. Our solar system, though seemingly peaceful now, harbors evidence of a tumultuous past, marked by violent collisions. The most prominent example is right next door, our own moon. The leading theory for the moon's formation involves a cataclysmic collision between a young Earth and a Mars-sized object called Theia. This impact, billions of years ago, ejected a massive amount of debris into space, which eventually coalesced to form our moon. This event, etched in the lunar surface and reflected in the composition of lunar rocks, is a stark reminder of the powerful forces at play in the early solar system. Further evidence of past collisions can be found in the tilted axis of Uranus, likely caused by a collision with a large object early in its history. The heavily cratered surfaces of planets like Mercury and Mars also whisper tales of a time when the solar system was a much more chaotic place. The aftermath of a planetary collision is a scene of utter chaos and transformation. The immediate impact results in shockwaves that reverberate through the planets, melting and vaporizing vast amounts of rock and metal. Debris, ranging in size from dust particles to moon-sized chunks, is ejected into space, forming a glowing ring around the remnants of the collision. Over time, this debris field can coalesce under its own gravity, potentially forming new moons or even rings around the surviving planet. The impact can also have a profound effect on the planet's rotation and axial tilt. For example, the collision that formed our moon is believed to have tilted Earth's axis, giving us our seasons. The impact on any existing life on the planets involved would be catastrophic. The extreme heat, widespread destruction, and long-term environmental changes would likely render the planet uninhabitable for a very long time, if not forever. However, in the grand scheme of cosmic evolution, these collisions, though destructive, contribute to the diversity and complexity of the universe.